Okay, we're live. We're live to air.
Yippee. Too hungry?
Yeah, yippee. So for today, I know some of you have moved on to the box project, and we noticed that there's a blueprint that goes along with the box project. So what I'd like to talk about today is a little bit about blueprint reading and the standards that they've come up with on a blueprint. So part of your handout package today is a actual blueprint. But before we move on, how many of you have put together IKEA furniture? Yeah. How many of you have seen like friends and family struggle with putting together IKEA furniture? Yes, right. So part of the challenge, one of the first things you do when you put together IKEA furniture is you get these things, the instructions. And if you look, it has remarkable similarities to an actual blueprint. There's hidden lines, there's pop-out boxes, there's call-outs, there's all sorts of like common things that you will see in a mechanical drawing in an IKEA drawing or an IKEA instruction booklet. So that's something that it's sort of a learned skill in the fact that if you can follow instructions, if you can follow the pictures, you can be successful with assembling a piece of IKEA furniture. Where the challenge often comes, can you guys be quiet? Where the challenge often occurs is you get mixed up. You don't know which way is up, which way is down, which way is left, which way is right. And so this print, they've come up with a standard. They've come up with a standard view on almost all mechanical drawings. This is your top view. There's your 3D view. So this is sort of a standard print that if I was presented in industry this part, I could follow the instructions just like IKEA and manufacture this part from scratch. And so the reason I printed it for you, if you look at the bottom right-hand corner, every drawing, every blueprint you will find, it'll have a header. Basically, what the part name is, who's making it, what's it for, who designed it, what the tolerances are. And if you look at the very, very bottom, or second from the bottom little row there, it says 2mm 304 SS. What do you think that means? 2mm 304 SS. Next. It means the thickness of the metal, 2mm, yeah. And what else does it tell us?
Oh.
Yeah.
The material. The
material. Yes. So right off the hop, we know that this part from Siemens is made out of 2mm stainless steel, 304 stainless steel. So right off the hop, we know what we're making the part out of. The second thing you're going to notice is this little that little image there, and that's part of your handout there also. That symbol means third angle projection. And the symbol is actually somewhat ingenious because it shows us how the drawing is projected onto the piece of paper. Just with that simple symbol. Then of course, and this is where blueprint reading and print making and engineering gets really complicated, is in this wonderful world we live in, there's two standard types of measurement. We have the inch system and the metric system, right? So we have two. And so looking at this print, is this drawn in inch or metric? Is this an inch or metric part? Because if it was If it was an inch part, it will be remarkably bigger than a metric part.
Yeah.
So if this is drawn in inches, this is potentially 262 inches long, which is what, almost 15 feet or something? So do you think this is a metric part or an imperial part, an inch part?
Metric.
Metric. If you read here,
This metric.
it says dimensions are in millimeters. So we know the material, we know the thickness, we know that this is drawn in metric. Metric is a common measurement in Europe. Siemens being a German company, their standard would be the print itself is drawn in metric. So this little header bar down here, it gives us a lot of information. The next thing that this thing identifies is the tolerances. The tolerance on a part is very important. If you can make every edge saw cut, not machined, just a really rough and tumble part, you can make it a lot quicker. Where this part appears to be much more intricate, much more detailed. So time is going to be spent making this part. A lot more time will be spent just because of the precision. We're at 2 decimal places, so this is a very, very finicky little part here. Another thing that you will find on a standard drawing is revisions. So for those of you who are working on the boxes, working on the sheet metal boxes, Ibrahim mentioned that he was struggling with bending and it was sort of creasing on him. Well, we might have to make a revision on Ibrahim's box if in fact he has to shrink it a little bit. So with a blueprint, if there's a change, and that's where recalls and defective parts seem to get derived from, is an engineer or somebody on the shop floor has made a change to a part and the revision doesn't get updated. So often, a part that has a revision along with it, it'll be labeled somewhere on the drawing to make sure that the new version 2.0, is the updated version that goes along with the part itself. So right there is usually on the bottom corner is usually where the revisions go. A little history lesson on blueprints. Why do they call them blueprints when clearly this is white and, yeah, Lena? There you go. Yes, they used to be blue in the 1900s when they first came out with the idea. Now, of course, this is drawn in CAD on plain white paper with black ink, but I still refer to them as blueprints. And obviously I wasn't around in the 1900s, but I'd say 99% of the prints that you will come across are done in CAD and saved as a file. And so if you look here, when parts get very, very detailed, and again, this is a physical print, but often when parts get very, very detailed, there's a chart that can kind of break down and decipher what you're looking at. So it gives you an added little bonus of information here of different features, different functions, different ideas of what the part should have machined on it. But again, very, very complex parts with thousands of little tiny details, you do have to have some sort of breakdown on what you're looking at. This part obviously is quite simple, but as you get more intricate and more detailed, sometimes it's necessary to break down the information. Getting back to the inch metric thing. When I worked in industry, I would often see very old blueprints. The oldest I ever saw was 1957. It was a really, really old part for an old machine. It was drawn in imperial. It was drawn in inch. Obviously before Canada went metric. But the one challenge that engineers and machinists and tool makers and welders, they often come across is the fact that because there's those two different measurement standards, that you have metric and imperial, you can't get those mixed up. And I read a story, and I heard about it years ago, where NASA got mixed up on, I think it was a Mars rover, and it actually crashed. And what happened was there was a mix-up between the angles of the descent. One was in metric, one was in imperial. So the lunar, or the spacecraft was, that's what it was. The spacecraft was reporting in metric, and the engineers at NASA were calculating it in imperial. And as you can well imagine, there was a discrepancy, and that Mars rover thing crashed. Another cool one was Air Canada had an issue where the ground, the fuel crew filled up the plane in metric, in liters, and the pilots calculated the weight of the fuel in gallons and pounds. And so they put less fuel than they were supposed to. They got up in the air and they ran out of gas. Now, fortunately, the airplane landed, but it's a really good indication on how important it is when you're looking at these prints and you're making these files, these blueprints, to make sure and double check that you call out the fact that you're working in metric or you're working in imperial. Just because when two parts built from two parts of the world come together, and one is giant and one is tiny, just because the scale of measurement was incorrect, and you go to bolt them together and it doesn't work, well, usually it's because it was drawn at a different scale. So for today, you're going to be looking at your box blueprint if you're ready to start on that. Tomorrow we're going to continue on with the third angle projection sheet. You can take a look at this tonight, and we're going to go through how parts and reality kind of go together. All right, so put these in your book. You're going to keep this handout for tomorrow, and we'll continue on with this blueprint. For now, you can get your stuff together and start working on your projects. Any questions on the blueprint stuff? Show of hands, how many of you have actually seen a physical blueprint like I handed out today?
Yeah.
1, 2, 3. Where'd you see it, Max? Where'd you get your hands on a blueprint? What about you, Isaac?
Lego.
Lego. Very cool. Yes. What about you? Oh, did you? Kinder Toys. Very good. Very good. All right. Thank you. 15 minutes.